this. But this is the Fourier transform exists in the sense of distribution. And no miracle, this function is continuous and everywhere of modulus 1. So it's a bit fixed. So this is an integrable distribution. It doesn't correspond to a measure, integrable function, or a measure, positive measure. And that's exactly the difficulty with Feynman passing. And that's, I mean, you have to replace e minus x squared by e I x squared. And so if you deal with ordinary Fourier transform and probability, it doesn't work. Many people have tried. At some point, it was not working. Okay. So that's exactly the meaning of our theory. So now we can also do this projection. For instance, if you have a Gaussian law in two variables, the probability density will be x squared plus x1 squared plus x2 squared. And when the projection means integrating with respect to x2 in order to keep only the dependence on x1. Or miracle, it's exponential by x1 squared. So now this is classical probability. But our definitions are such that it works for integrable. If I take an integrable distribution, the same formula holds. That means now I take for f2 a test function on e2. I have to match f2, which is a test function on e2, with something. And by definition, I take f1, which is a composition, and I replace m1, so I replace t2 and t1. And that makes sense. If you have a test, the point is that if you have a test function on less variable, if you have a test function in one variable and you put dummy variable, it's still a test function in this complete set. So that's exactly the crucial point in our definitions. Okay, now just to say that was important, just to remind you of I tell you some idea of Borner. Something written around 19, maybe around 19. As Borner is known for his Borner theorem, which characterized the Fourier transform of a probability law. That is very important, very important. He wanted to generalize this to a system of infinitely many random variables. So, suppose that you have a system of infinitely many random variables, independent or not, in the classical sense. Now, if you the projection Pn, so this is this sequence, infinite sequence. Pn is a truncation keeping only x1 and 2xn. So it's a random vector in n-dimensional space. Now, a random vector in n-dimensional space has a probability of un, which is a probability law in Rn. And by the very definition I gave above, if the system un should be consistent, that means that if you have un, which is a probability measure on Rn, or un plus 1 on Rn plus 1, then you consider the projection of Rn plus 1 onto Rn, which omits the last coordinate, x1, xn plus 1, goes into x1, xn plus 1, removed. Then the corresponding projection should be un. If you have the probability law for x1 up to xn plus 1, if you forget xn plus 1, you get the probability law for x1, xn. So the probability law of such an infinite sequence can be described by giving the so-called marginals marginals, which are measured on finite dimensional spaces, probability of finite dimensional spaces, and a consistency condition, which is that the projection Pn of mu n plus 1 is mu, consistency condition. But now there is a well-known theorem by Kolmogorov, which says that with a proper definition of integration in infinitely many dimensions, and that was provided by Sachs at the time, you have a measure on infinite dimensional space. So you have a measure of mu infinity on the space R infinity. What is the space R infinity? The set of all infinite sequences without any restriction. They can explode as you want. So in general, you are not interested in that. For instance, you are interested in having, in the Gaussian system, you are interested in the sequence which satisfies sum of the xn squared being finite. And you can prove that if you all the mu n are Gaussian, and if all the variable x1, x2, x3 are Gaussian independent with the same law, Gaussian independent with the same law. That means formally you have the product of E minus pi I x n squared dxn, product over n. So you are tempted to say, well, it's simply E of pi sum of xn squared d infinity x. D infinity x is a product of the dxn. Well, but the difficulty is that it can be shown, it was known to Paul Levy already, that if you take an infinite sequence of independent random variable, each following a normalized Gaussian law, used by normalization, then the sum of x n squared is almost everywhere plus infinity. With probability 1, the sum is plus 1. So you cannot, this with probability 1 is exponential minus infinity, which is 0. Doesn't exist. So the point is that that's one of the difficulties. And so Borgner tried to cope with this difficulty by working, instead of working probability law, he was working with the Fourier transform, the characteristic function sense of probability, and that makes sense. Okay, but, and now we took advantage of that. Now, important, and I can finish. Now, that one was finished. We are interested not in E minus x squared, but in I x squared. So what we do, we don't know, we use this strategy. So now we have some infinite dimensional space. E is an infinite dimensional space. And we would like to, with some properties, let's say a normal space, a Banach space. In many applications, in our application to quantum mechanics, the space is a space of paths with finite action, which means that finite free action. That means you have x of t, for t running from ta to ti, the initial to tf, and we assume that the integral of dx squared over dt is finite. Or more precisely, that you have integral of x dot squared dt. Well, x dot is dx over dt. But it's better to write it formally like that. X dot, that's the action, the free action. And you assume that xt has a finite free action. What does it mean? It means that the function is absolutely continuous in the sense of the name. the derivative existing almost everywhere is square integrable. And that's a well-known Sobolev space. It's the first among the hierarchy of Sobolev spaces. Our notation is L2-1. L2 because our square integrable function, 1 for the third derivative. Function whose third derivative is L2. And distribution can help to define this. So, okay, that's typically the space we want. And the norm, of course, the norm will be, the square of the norm will be that. It's not only a Banach space, but a Hilbert space. So we have an infinite dimensional space. We introduce E prime, which is a Banach dual. That means for linear functional which satisfy f of x is bounded by a constant depending on f, the norm of x. Banach dual. And now, what we do, we pretend to define something existing on E, but what we do, we define the Fourier transform on E prime. Fourier transform on E prime. And so, for instance, in the space, and so, in the space L2-1, we can, the Fourier transform can be, of course, the Fourier transform can be extracted by the action, that's the action. And what you have is that really you have a Fourier transform is something like I, the norm square of y squared, for y in E prime, and f. So, it has, if you do formally the calculation, either in this sense or in this sense, you will find that formally it's EI sum of the coordinate x squared dx. What do I mean by dx? It's a distribution. It's a distribution on Hilbert space. That means it integrates certain test functions. Now, when I write dx, it means that if I write formal integration, sum f of x ex ds, such an integral means the following. I take a suitable function f of x, I integrate it by my object, but this object I write it formally as I equals I squared dx, y, because there are transformation law which obtained from the Fourier transform, which are the Cameron-Martin space. There are well-known Fourier transformation property for the union motion, and so that, I mean, if you just want to translate f(x) and replace the variable by x plus a constant, you want to see how the integral modifies, but it modifies formally as you transform x into x plus c, and that's all. So if you want to integrate fx plus c with respect to my distribution, call it theta, then it's behaved formally as to you have fx plus c, so you have x plus c. Now you replace x by a minus c, you have that minus c and c dx. So the point is that according to manipulation with Fourier transform show you that the transformation property under translation of our object, our integrable distribution in infinitely many dimensions, behave as formally as if you had this expansion. That means you manipulate this as a way explained. And so finally you have a dx, which is a formal symbol, which has a property of being translation in there. So it behaves like formally as a product of all dxn. The product of all dxn should behave in this way. If you replace one of the variables or any of the variables by a constant, adding a constant, you don't change the integration process. And so it means, since we are interested not in dx itself, but in some expression of this kind, it gives you a transformation loop that we can prove using property of Fourier transform. So, at the end, we have, for a suitable, the final result, we define explicitly a class of functionals, of test functionals, which depends, x is the trajectory of the path of your particle, or it's just a realization of your field, a sample of your field. So you define a very precise class of test function, and you can define an object which is formally of this type, which has all the properties that you expect if you write it in this form, and you apply your common sense to that. So that's what you can. Now, what is the difficulty is that our class of functional is quite large, but not large enough. So in many cases, we can give a formula, we can give a rigorous meaning to such calculation. But at the moment, we believe that the class of test function is too small, and certainly there are examples which are not covered by that. On the other hand, I mean, if you have if f of x depends on a parameter, the smoothness property of the dependence of the integral are not yet established. And at least in some cases, you have some easy cases, but there are difficult cases which are connected with, let's say, the convergence of the perturbation expansion. At the moment, you can see this. Thank you very much.
Thank you very, very much. So we have time for a few questions, and then we should go for lunch.
In the class of functions f, you are allowed to do all the computations. Can you prove the other properties of an integral? I mean, the important thing is integration by parts.
Yes, that's.
So integration by parts can be done. So in principle, one can prove
integration by parts.
You can prove stationary phase.
Yes. No, integration by parts. Because I told you, integrable by part just amounts to derivative on one side, on the other side is multiplication, and that's how. I said that my object, my integrable distribution, I gave the formal definition when you have finitely many variables, but it's phrased in a way which extends immediately word for word in the infinite dimensional situation. You are able to integrate by part. That's perfect.
What's the relation of your theory with the Kohn and Kramer? Is there any overlap?
It's difficult. I mean, in this approach, we don't address the question of renormalization. So that means it works for theory which don't need renormalization, or what's that say? Basically, two-dimensional field theory works perfectly. I mean, but it's what people did in the constructive field theory long ago. So we cover that. I mean, we cover that, and in many cases we don't have to. Well, what people did is to go from -1 to I by a process of analytic continuation. So if you have if you put S x squared, and you take S as a complex variable, and sometimes it's -1, sometimes it's I, and you do analytic continuation. Many people have done that. So they have been able to reduce this kind of calculation to standard calculation with probability theory using standard Wiener measure, which is well established. And so, so we can repeat most of the things which were done, with maybe not so precise at the moment. The work in functional analysis has to be done to recover directly without an analytic continuation the result of the people in constructive field theory. At the moment, no one did that. I don't know if it's really important to do it at the moment. But renormalization is totally different subject. And Kohn and Kramer have done a very beautiful algebraic description of renormalization. And I will speak of that too. So it's another subject. At the moment, the main difficulty, what all the physicists know, is that we cannot do field theory in a realistic situation without renormalization. And I don't know how to include renormalization in this frame. We have a chapter, in our book we have a chapter on renormalization, but which is just it's a thesis of one of our students, Marcus Berg, but which is included in our book. But it's it's still a mystery, I would say. It's still a mystery.
Sherry?
Do you have enough under control to justify the extraction of the Feynman diagram formulas?
Well, if in a theory which is, it doesn't need renormalization, we have it. But as I said, it's a challenge. And no, I mean, for instance, I mean, we should be able to do something in a nonlinear situation that, let's say, in a two-dimensional gravitation theory. So maybe we can apply this to two-dimensional quantum gravity. But two-dimensional quantum gravity is very far from what we expected. So it means that much more remains to be looked at.
Okay. So that's